Good morning, everyone, and welcome to the Bioimage Analysis course. I'm more used to more interactive talks, so I will try to leave quite a fair time for the discussion and go through the slides relatively quickly. The topic of this first talk is basics of image, what's anatomy of image, what makes an image, and we will discuss what differentiate images or data from pictures, and then a little bit of the different parameters that can define a picture. Image is just an array of information. It tells you how much light you have and where you have it. In the simplest of cases, we have black and white pictures where each pixel codifies of how much light this pixel contains, and in the 2D case, this is mapped on a plane. Here we have as an example a picture of a Fabio, and the picture of Fabio will follow us through this talk as we discuss the different aspects of images. Image is an intuitive way to show two-dimensional data. The data could be, for example, intensity of a fluoro for a given part of the cell, or this data could be Leonardo's Mona Lisa, or this data could be Fabio. Here we have taken a close-in picture of Fabio's pecs, and here we can see the pixels, and while in this picture we can see the muscles and the shadows between them, what in reality we have is just an array of numbers. The array of numbers is the data we have, and the picture is how we represent it to the human viewer. We saw that the Fabio's muscle was made up from numbers between 80 and 200. These numbers are actually arbitrary, and they have to do with something called Bitdeath. The Bitdeath explains how many values we have between the black and the white, where the black has the lowest value and the white has the highest value. We will discuss this a bit later. The values between the black and white are of course grays, and they form something called a grayscale. Black and white images are also known as grayscale images, and as the name implies, they have some white, some black, and a lot of gray in them. When people first began creating computer screens and printers, they had several considerations. Firstly, they had to think how many different kind of grays they can show on the monitor, or how many different kind of grays they can print. And secondly, they had to consider how many different grays human eyes can see. Let's take black and add white until we get pure white. And let's do these additions in x steps, where the x is 20, 50, 100, and 256. Here we have the example with the 20 grayscales, where we start from the black, and then we add white until we get to the actual white, going through 18 different levels of gray. On the right, we have done the same in 50 steps, where we go from black to white in, 50 steps. And here we have 100 steps, and here we have 256 steps. As you can see, the transitions become smooth somewhere between 50 and 100 steps. Should we worry about the shades of gray? Should we worry about how many levels of gray in the picture we have? Sometimes we don't. If we just want to show something that it exists, whether this is your grandmother, your cat, or Fabio, or whatever is the biological equivalent of Fabio, you can do whatever your machine does. On the other hand, if you plan to quantify your data, say if you want to compare the intensities, or if you want to do colocalization, or if you want to do some measurements on the morphology, you need to be worried, because now the different values are measurements and not just a random image. Microscopes are high precision instruments, and they can usually acquire an image with various bit depths. That is to say, you can decide how many numbers you have between black and white. If we have an 8-bit image, we get to have 256 grayscales. If we have a 12-bit image, we get to have bit over 4,000 grayscales, and if we have 16-bit image, we get to have 65,536 grayscales. Now, as you might remember, the 8 bits will already give you a smooth image to your human eyes. The additional bits only matter if we are actually measuring the signal somehow. The bit depth represents the accuracy of division between white and black. The more bits we have, the more shades of gray we have, and the more minuscule differences we can show. Most images you see in the wild, that is on the newspapers or online, are color images or RGB images, where the RGB stands for red, green, blue. And these images are basically 3 grayscale images layered on top of each other. So each pixel has 3 values that code how much red, green, and blue that pixel has. Now, Fabio here hopefully demonstrates this pretty well. On the red channel, we can see that Fabio's face and chest are really bright. This is because his chest is largely red. On the blue channel, we can see that his genes are bright. That is to say, the genes have a lot of blue in them, and lo and behold, the genes are actually blue. His coat is black, so it has little intensities on all of the channels, which makes black. You might notice that the blue image here is notably harder to see than the black and white version of the blue image here. This is because the colors are not equal in our eyes. The human eyes, or probably eyes of all mammalians, have evolved to see a green better than any other color. This is probably because at some point, when we were monkeys living in trees, we had to find green fruits among the green leaves. We never ever had to look for something blue amidst something blue. So whenever you portray your data to the viewer, avoid showing anything important in blue, because human eyes cannot see blue very well. The images you get from the microscope are not color images, even if they look like that. In reality, the images you get from the microscopes are overlaid measures. So we first measure, let's say, the red signal, then we measure the green signal, and then we measure the blue signal. The microscope does not know what's the actual color coming out. The microscope only measures intensity. And when we want to show these intensities on top of each other, we apply colors to them. We say that, okay, this intensity is mapped in red, this intensity is mapped in green, and this intensity is mapped in blue. And now we can put them on top of each other so we can see how the intensities relate to each other. You might be inclined to think that there's no difference between the image of Fabio and the image of cells. They are both called images in the everyday language. However, the image of the cells is data. It's a measurement. And as nice as Fabio might look, he is not data, nor is he a measurement. He's just a picture. And while you can snap pictures with your phones as freely as you want, you should really take a great care when you are acquiring data. basically you should think that every time you use a microscope to take a picture, you are doing a precise measurement. You are merely not snapping a picture. The same rules do not apply to pictures and data. A picture where you cannot see anything is pretty much useless. A measurement where the computer can still see things even if you cannot see them can still be useful in some cases. So be careful not to judge your data on the criteria you might apply to pictures. Your data might look crappy, but it might still be highly useful. Next, we're going to discuss resolution and sampling, and they detail how precisely you can represent the reality using an image taken with a microscope. The physical size of your pixels affects the quality of your signal. The larger the pixels you have, the more fluorophores you can have under that pixel, and then the more signal you will get out of it. So the smaller the pixels we have, the less signal we have per pixel. This brings us to the matters of sampling and resolution. Sampling basically means how big pixels you take. There is a physical optimal sampling where you basically do some mathematics, figure out what is the best your system can do, and then follow that. Then we have something called oversampling, where we use smaller pixels than physically possible. This is usually done if you want to deconvolve your pictures. And then we have something called undersampling, where we use larger pixels than the optimal ones. And as bad as this might sound, there are many cases where undersampling is a valid strategy. If you want to count cells from your sample, you do not need the optimal sampling or the physically optimal sampling. So the best possible sampling and the physical optimal sampling are not the same thing. You should choose your sampling according to your image and your needs. In simple terms, the sampling means how many pixels we are using to portray information. The higher the sampling, the higher the resolution, the higher the amount of pixels we are using. Here we have a high resolution Fabio and low resolution Fabio. As you can see, the pictures themselves look almost the same. Only when we look in closer at his muscles, we can start to see that the low resolution Fabio shows pixels and the high resolution Fabio is smooth and precise. But as you might see, in the case of Fabio, this doesn't really matter because we are trying to show something this big, and in that case it doesn't matter if this distance is 2000 or 500 pixels. And now we're going to discuss resolution, what the resolution actually means. Sometimes you see that people say that they are taking pictures in 512 resolution. This is not resolution, this is image size. Also, zoom is not resolution, even if the zoom tends to affect the resolution. Pixel size and resolution are married to each other. You cannot achieve the best possible resolution without the best possible pixel size or sampling. However, smaller than the optimal pixel size does not improve resolution. Resolution is defined as an ability to differentiate objects from each other, and this is something you should try to remember. So here we can see a cell with, let's say, 2 vesicles, and the vesicles are red, and then we have 2 different samplings. On the left we have sampling number 1, on the right we have sampling number 2. As you can see, the sampling 1 fails to differentiate the 2 objects from each other because each pixel we measure has red in it, and then it will record as a red in the final product. On the image on the right, we managed to have some pixels without any red between these 2 objects, and then in the final image these 2 objects will show as different objects instead of one object here. and this is the definition of resolution: the ability to differentiate structures. Resolution is the ability to resolve structures. Resolution is usually given in nanometers, and it's basically a measure of how close you can have structures and still see them separate. Your pixel size might be, for example, about 70 nanometers, but that doesn't mean that your ability to resolve things is 70 nanometers. The rough equation for XY resolution reads: your resolution is hat times lambda divided by NA. Here lambda is excitation wavelength for confocals, and perhaps a bit confusingly, emission wavelength for wide field systems. The NA is the numerical aperture for your objective, and the hat is a multiplication factor that depends on the modality of your microscope. And I will note that this is the simplified equation, and we will not discuss the actual true equation as it's quite convoluted. The equation shown on the previous page has few immediate consequences. Firstly, the bigger the NA you have, the smaller the R will be. Secondly, the smaller the hat, the smaller this guy goes, the smaller the R goes. Usually the values for the hat are 0.4, 0.5 or 0.61 depending on the modality. Also, you should notice that the wavelength will affect your resolution, so that the smaller wavelength gives better resolution. The different values for the hat come from different theoretical models based on Bessel functions, which have been used to model the propagation of light, and this stuff is way beyond the scope of this course. It suffices to say that somebody has done the math, and you don't have to worry about it. As complex as it is, it's not magic, it's just physics. For the confocal, the hat is about 0.4, and for the wide field, the hat is about 0.61. You might remember that the equation we have been discussing described the XY resolution. The Z resolution, or the resolution in the direction of the depth, reads that the resolution equals to different hat multiplied by lambda multiplied by n divided by the NA to second power. Here the lambda is again a wavelength, the hat is some mathematical constant, the NA is the numerical aperture still, and this n here is the refractive index of the medium between the lens and the specimen. So if we have our objective here, and here we have our cover slip, it's the refractive index of this stuff here. And for the confocals, this new hat is about 1.4. Recalling our equations for the depth resolution and the XY resolution, and assuming that we are working with the green 488 excitation laser, we can tabulate the optimal resolution for some commonly used objectives. For 63 oil, we can get XY resolution of 140 nanometers. For 63 glycerol, we can get about 150 nanometers. This is because of the lower NA. And for the glycerol 20X, we can get XY resolution about 260 nanometers. And then the Z resolutions will scale in kind. It should be noted that while oil objectives give nominally better resolution, the aberrations caused by refractive index mismatch will likely undo any potential gains as long as you're using conventional mounting media. The exception to this is a new prolonged glass that has a refractive index of 1.52, which you should use with oil objectives. As we discussed before, the optimal sampling and the optimal resolution are not the same thing. You can find often a recommendation that your pixel size should be 2.3 times smaller than the optimal resolution if you want to resolve your image as accurately as possible. And this can be thought as a way to make sure that you can fit a pixel between your two structures you're trying to resolve. If you have more than 2 pixels between the minimal distance, then you should be able to fit in 1 pixel that will remain dark, and then you can still resolve the 2 objects as separate. And if we apply this 2.3 to the numbers we computed on the previous page, we can get the optimal values for the XY sampling and the Z sampling for the different objectives. And we should have at least 20 minutes for your questions. So please ask if you have anything on your mind. As said, I'm more used to a more interactive talks where I let people ask things as I'm presenting the slides, but as it's not an option here, we'll have to go through your questions now. So please ask if you have anything, and I will try to answer your questions as best as I can.